So this is the last part of the talk, and the part that's a little bit more technical, I guess. I hope it's going to be interesting to you guys. This is about our reworked conformer model. So the conformer is just the latest version of the transformer that everyone is using in speech recognition. And what it is it's just the transformer plus a convolution module. But so our reworked conformer is the conformer with a lot of changes that I'm going to describe below. And it allows us to have faster training and more stable training and slightly better order rate. But I think the main reason I think you'll be interested in this talk is that we have some insights about things that can go wrong with transformer training. So here is a picture of the conformer encoder. This is the main part of the transformer. Yeah, it's a modified transformer. So in each layer, in each module, we have a feed-forward module, then self-attention, then a convolution module, then feed-forward. So if you just have the first two, the bottom two, that would be a standard transformer. Now, so the red part in this diagram is the LayerNorm. We use so-called pre-norm, that at the start of each module, there's a LayerNorm, and also at the output of the whole layer, there's a LayerNorm. Okay, so former BatchNorm inside the convolution module, and also we were using BatchNorm at the input to our we were originally using BatchNorm at the input to the whole thing to normalize the speech features. Now, so I'm saying that BatchNorm should be considered harmful. And here's the reason. BatchNorm itself works great. Like, there's no problem with it. But the problem is, if you do anything unusual, BatchNorm is going to create a lot of problems. So if you group the training utterances by length, that's going to be a problem for BatchNorm, because BatchNorm has this assumption that the elements of the mini batch are sampled independently. So if you do something like you group the utterances by length, or maybe you have two different data sets and you want to do them in different mini batches for some reason, this is going to cause a lot of problems with BatchNorm. Basically, it's going to affect your results, because it's a train test mismatch. That in training time, your model is seeing utterances that are grouped in a non-random way. And then in test time, because we use the average BatchNorm stats, it's as if the utterances are grouped randomly, and it will affect the results. Also, if you do fine tuning on a different type of data, it's going to be a problem. It's actually ironic, because in the original BatchNorm paper, they say it's a solution to covariate shift. And covariate shift just means that you have a different type of data that has, different distribution. So this is actually the thing that BatchNorm cannot deal with, that if you have a different data distribution on different parts of your training and you separate them, actually BatchNorm is really bad at dealing with that. So anyway, my position is that if possible, it's going to save you a lot of headache if you just take BatchNorm out of the model. So one of the first changes we made to the model is to just replace BatchNorm with LayerNorm in the convolution module, and also for the input to the network. And in the input of the network, actually, instead of LayerNorm, we just replaced it with a scale of 0.1. So the reason that's necessary is because the log-mel features have a very high dynamic range, like -20 to 0. And because that's so large, the the bias parameters cannot really get large enough to be comparable to that. Like if you multiply this -20 to 0 by a weight, it's still going to be large, and the bias can't train big enough. So we just replace it with a scale. Now, a lot of you are probably thinking, why are you using log-mail features? Everyone is using the waveform. Now, a lot of people do use the waveform as an input, and of course it's great to use that, but it doesn't really give you any advantage. A lot of people have published papers in conferences like NIPS saying, oh, we have this thing and it's better than log-mail Kepstrom. But usually there's some problem with how they did that comparison. And whenever anyone does like a reasonable comparison, it turns out it's not really better. Now, this may not always be true. Maybe in future, someone is going to really show that it's better to use waveform. But we use filter banks because they're more compressible and you can load them much faster from disk. Otherwise, you become limited by I/O. Anyway, so the next thing is we'd like to remove LayerNorm. Like if you look at this this model, it seems like there's too much LayerNorm. So let me get into why we need LayerNorm, and I'll maybe be able to explain why I think it has too much LayerNorm. So let's recap what LayerNorm is. So LayerNorm is just a formula applied to a vector that could be like one frame of speech or one pixel of an image. So it has 3 stages. We remove the mean, which is actually a waste of time in most cases. We normalize the length of the vector, and there's an epsilon in that formula. And then we apply a learned per dimension scale and offset. And this is the same as in BatchNorm, like a weight and a bias. Now, why do we need LayerNorm? So in a deep model, unless you normalize every so often, eventually the activations are going to become like infinity or 0. And then your training is not going to be stable. It's going to fail. So in addition to the normalization, the learnable per dimension scales, the gamma, those help to balance the size of the activations and the relative contributions of the different modules. So there's 4 modules per layer, right, in the conformer. Now, we want to be able to scale up or scale down each individual layer. And it's very hard to do that by learning the size of the weight matrices of the layers, because they're so large that to scale them down, you're basically trying to learn a very high dimensional direction, right? It's too hard to learn. So it's much easier if you have like a separate scale, like the per dimension scale and BatchNorm, that you can just scale down the output of that module to balance the contribution of those 4 things. So that formula shows you how, just due to the noise of the gradient noise from each mini batch, this is how the size of the weight matrix will change over during training naturally. If the learning rate is constant, it'll follow like a square root of t line. And actually, if you look at the weights in transformer models, you'll see that they're quite close to this formula. Now, this formula is only valid if the optimizer is Adam with no weight decay. With weight decay, you have to compensate. But the point is, it's better to just let the weight matrix naturally do its thing and get larger and larger, and have something else that's going to scale it down. And that's where the BatchNorm or LayerNorm comes in. Now, there's certain bad things that can happen during transformer training. In our IceFall, we implemented a lot of diagnostics, so PyTorch has these forward hooks and backward hooks that you can add. So it's possible to use those to accumulate a bunch of statistics to tell you like how big the outputs of the different modules are. Now, so that's how we discovered certain problems that can happen in transformer training. So you can get whole modules dying. So this means that, let's say one of the feed forward modules, after training, you'll see that the output of the module is almost zero. It's like 10 to the minus 6, something like that. And that seems to be something that happens with the BatchNorm weights. So if early in training that module was not useful, the BatchNorm weights go almost to 0 to turn it off. And the problem is, if the BatchNorm weights are oscillating around 0, they're becoming positive then negative. The module never learns anything useful because the sign of the gradient is constantly flipping, right? So it doesn't know which direction to learn. So basically, in that case, the module never learns anything. And this happens particularly for the lower down feed forward layers. It can happen for quite a few of them. Now, there's another odd or undesirable thing, perhaps, that happens with LayerNorm, that especially in the middle of the network, after training the model, we notice that often one channel out of the, let's say, 512 or 256, one channel gets very large and constant. So you look at the activation and it's, let's say, negative 51 plus or minus 1. So it's almost constant. Now, the individual modules don't really see this large activation because it gets scaled down by their input input layer norms. And my belief is that the reason the system does this, the reason it learns this large value, is it doesn't want to get layer normed. So layer norm removes the length information, right, from the vector, because it normalizes the length. The model doesn't want that, so it adds this large constant value, which functions like a very large epsilon in that formula, and that means that the length of the length of the rest of the vector elements, excluding that one large value, is almost constant at the output of the LayerNorm. So we're going to use this insight to help to replace LayerNorm and to fix this problem. So this negative large value is going to be a problem if you want to use let's say integerization. If you want to use 8-bit activations, it's going to be a problem to have this big large value. So so here's how we removed LayerNorm. There's a few things that we had to change. Firstly, remove LayerNorm at the inputs of the modules, and at the output of the whole layer, we replace it with something called basic norm. So basic norm is just, we normalize the length of the vector, but we normalize it with a large epsilon. So this epsilon, like, we initialize it to 1 and we learn it in log space. So in the end, it's going to be like 2 or 4 or 5 or something. So what that does is that because the square root inside it is dominated by the epsilon, the output vector length doesn't strongly depend on the input vector length. We know that it's going to be shorter than 1, but sorry. The output vector length does depend on the input vector length, meaning if the input vector is longer, the output is going to be longer. Now, because we need to balance the contribution of the different modules and we don't have the learnable weight, we modify all our weights and biases by, instead of self.weight, we use self.weights times weight scale.x. So we're multiplying it by a learned scale, but that scale can only be positive. And it's important that it should only be positive, because otherwise we can get the oscillating gradient problem that I mentioned before. So if the scale is going negative, positive, negative, positive, we never learn anything because the gradient keeps flipping. Okay, so that's how we remove LayerNorm. Now, we made some other changes to the model too. So there's another failure mode, or another bad thing that can happen during model training, is inside the feed-forward modules, and there's 2 feed-forward modules per layer. A lot of neurons can die. And what that means is there's a hidden dimension inside the feed-forward. Let's say it can be 2048. We might find that 10% or even 50%, even 80% of those neurons are always negative. Now, the activation is very similar to ReLU. It's actually something called Swish, but it's ReLU-like. And if the activations are always negative, the output is always 0, or at least always close to 0. So it's not doing anything useful. So we have a way to fix this by modifying the gradients. I'll explain it later. There is another failure mode that's less common. Again, we discovered this by looking at the diagnostics that I mentioned. So the actual activation inside the feed-forward modules, and also the convolution module, is something called Swish, that in PyTorch it's called SILU. It's just x times sigmoid of x. Now, if the model is well trained, you'll see that the normal magnitude of the input to this SILU will be between about 1 and 3. That's the root mean square value of a dimension. Now, there's 2 ways that the model cannot train properly. One is if the inputs become too small, like 10 to the minus 4, 10 to the minus 5, the function is almost linear. Like if you scale up the function, it's just y equals x. And in that case, it's not learning anything useful. There's no nonlinearity. The other problem is the inputs to the function can become very large, like 100. In that case, it's just the same as ReLU, because if you zoom out from that, it's the same as ReLU. And that's not optimal because ReLU is not quite as good as this Swish. So again, this is something that we're going to fix by detecting it and messing with the gradients. So yeah, our solution to both of these problems that I mentioned just now is something called the ActivationBalancer. So this is a module that does nothing in the forward pass. In the forward pass, it's just y equals x. And in the backward pass, it's going to modify the gradients a little bit. Now we place this module just before the nonlinearity, meaning just before the Swish. And what this module does is, in the forward pass, it does nothing, but it accumulates some statistics, and it works out which channel dimensions are problematic. And problematic means, for instance, less than 5% of the values are more than 0. This 5% number actually comes from CalD. We used to do the same thing in CalD. So for those dimensions, we want to penalize them if they're negative. Now, what we discovered in early experiments is that if you just add a penalty to the loss function, what the model does is it just concentrates all the positive values in the padding frames, because the utterances have different lengths, right? We have to pad with 0. So the model learns to just make those padding frames very positive. So that's not what we want. So instead, we fix this by modifying the backpropagated derivatives by multiplying them by 1 plus epsilon or 1 minus epsilon. And which one we choose depends on the sign of the input and also the sign of the derivative. This, you can work out what the rule is. It's quite simple. And we also use a similar approach for the wrong magnitude problem. Like if the mean absolute value is less than 0.2 or more than 10 or something, we can use the same kind of formula with epsilon to encourage the inputs to have the magnitude that we want. Now, there's also something quite cute that we discovered accidentally. So at some point, I had a bug in some script that was applying the swish nonlinearity twice. And I noticed that the experiment was a little bit better. Like after I fixed that, it got worse. So I'm like, why is that? So it turns out that it's actually a better nonlinearity. I'm calling it DoubleSwish because it's just swish of x, but you can approximate that function by x times sigmoid of x minus 1. It's an almost identical function. If you look at that figure, those two lines very close together, one is one and one is the other. So we're actually using this sigmoid of x minus 1 times x. It gives a very small improvement. It's like 0.1% whatever rate, but we've validated it in a few different setups, and it seems to be consistent and real. Yeah, so this is just a larger version of the figure showing the new nonlinear. It's not just a scaled version of swish. It's actually it's qualitatively different because the derivative at 0 is 1/4 instead of 1/2. And eventually it becomes just linear, like y equals x, but the behavior around 0 is different. So, okay. So there's another problem that we fixed, and you can argue that maybe this is not a problem, but I didn't like it. So as I mentioned before, the parameter tensors will naturally grow throughout training. Just because each iteration gives you gradient noise, and that gradient noise adds up during the entire training. Now, one way to fix this is just to use the learnable scales in BatchNorm and LayerNorm to scale things down. And that kind of works, but eventually it can become unstable because once those BatchNorm or LayerNorm scales get very close to 0, the output can become too sensitive to them because the big tensors are too large. So eventually, after training many iterations, your transformer or conformer can suddenly become unstable and go to infinity. Another reason I don't like these growing parameter tensors is it makes the learning rate schedule very hard to interpret. Because what can happen is that even though the learning rate is growing, you're actually learning slower and slower in relative terms because the parameter matrix size is growing even faster than the learning rate. So yeah. So our solution to these varying parameter norms is we just limit the root mean square value of all non-scalar tensors to 0.1. And we do this by, if it gets larger than that threshold, we start to apply weight decay. So this is just a change to Adam. So if you take Adam W, which is just Adam with shrinkage for the weight decay. So instead of modifying the gradients, you just shrink the whole parameter matrix. That's Adam W. So we change that to Eve, which is we only apply the shrinkage after you get root mean square more than 0.1. So this makes the learning schedule much easier to interpret. But we also, sorry, We also have to use a different learning rate schedule because the conventional one doesn't work anymore, right? So we have to decay it more aggressively for large T. So here is the standard learning rate schedule for transformers. It's something called a GNOME, or sometimes people call it just a transformer learning rate schedule. So it starts to increase linearly, and then it decreases as 1 over square root of T. And what you'll find is if you try to train a transformer using a conventional learning rate schedule, it just won't train. It will never learn anything. I mean, certainly that's true for speech in our experience. So we actually, as part of this rework of the conformer, we're removing the warm-up period. And instead of warm-up, we implement warm-up at the model level. So that arrow around the side, the curved arrow there in the picture, that's indicating a layer level bypass. So what we do is we have this constant called a warm-up that we feed it into the model, and it begins at 0 and increases to 1, and then it stays at 1. So for the first 3,000 iterations, this warm-up is increasing. And basically, for each layer, we bypass the layer proportional to warm-up. So look at that formula there, 1 minus warm-up. Oh, sorry. I'm trying to highlight that, but it's not working. We return 1 minus warm-up times input plus warm-up times output. So effectively, if warm-up is close to 0, the model acts like a very shallow model, and it's much easier to learn. And after we make this change to do the model level warm-up and use a different learning rate schedule, we find it optimizes way faster. So our learning rate schedule that we after tuning this, here is what we came up with. I'm putting in like actual constants. These are obviously tunable, but if n is the epoch and t is the mini batch from the very start of training, including all epochs, this is the formula. It starts off approximately constant, then it becomes like 1 over square root of t, and then eventually it decreases like 1 over t. And the reason we make it dependent on both the mini batch index and also the epoch index is it gives us a better kind of invariance when we change the mini batch size or the number of workers. So basically, we want to have about the same rate of progress per epoch, regardless of how many workers we have. So if we have more workers, we want to learn a little bit faster per mini batch. And this formula gives us the right kind of invariance. So the idea is we just tune it once, and then when we change the number of workers or the mini batch size, we don't have to retune it. So this figure just compares, the red one is our formula, and the orange one is the standard transformer learning rate schedule. You cannot really, in a sense, you cannot really compare these two because they're intended for different types of model. Our thing is with the fixed parameter norms. So in reality, the transformer learning rate schedule is decaying faster than that because the matrices are getting larger, so the relative change is smaller. We did notice that after you fix the parameter norms, the learning speed becomes much more sensitive to the exact learning rate schedule. The reason for this is that if you don't fix the parameter norms, if you use a larger learning rate, your parameter matrices get larger, right? So the relative change in learning rate is smaller. And in fact, if you multiply the whole learning rate schedule by 2, you'll train faster initially, but for large T, you're actually training about the same speed because eventually the parameter matrices will just be twice larger approximately. And it turns out you can do some analysis on this using the formula that I mentioned previously. Even if you have a T to the P type schedule, even if you change that power, if you think about if you work out the relative learning rate, in theory, you're really just changing it by a constant factor for large T. This is true only for P is greater than minus 0.5. You can work out this from the formula that I mentioned a few slides earlier. Oh, I can't find the slide. It's that formula with a square root in it. So anyway, the point is that even though the transformer learning rate schedule looks very weird, it's actually not as weird as it looks, because even while the learning rate is increasing, it's actually learning slower and slower, at least once it grows beyond the initial parameter size. So this graph shows the speed of convergence of our new model in blue compared to the old model in orange, and you can see that for the first part of training, we're training way faster, like 10 times faster or more, because we don't have this warm-up period and we have this model level warm-up. It's way faster, and even later on we're still faster. It's like maybe twice faster, or at least 60% faster. Sorry, I mean 40% faster, something like that. So we also have some small error rate improvements. Unfortunately, so all the things I mentioned above, I tuned those on a smaller subset, like LibreSpeech 100, and it turns out that not all of those changes are fully additive. But when we test the whole thing on LibreSpeech, on full LibreSpeech, we still get an improvement. And the main improvement of all of these things is the recipe is more stable and it's way faster. Like, for a start, we don't need so many epochs. We're using like 30 epochs instead of 60. And also per epoch, it's a little bit faster because we took out all of those LayerNorms. Plus it's more stable. So we're also working on a further improved version of this optimizer, where we use the scatter of the gradients to do a change in coordinates before we do Adam. So because Adam is per element, if you rotate the parameter space, it actually is going to change. It's going to change how it behaves. So, but I'm not going to describe that right now. It's not really finished. Okay, so this is just a summary of what I've said before, so that to help you guys remember it. First, I had this argument that BatchNorm should be considered harmful because it causes hassles for things like fine tuning and data loaders. Second, we replaced the LayerNorm with this basic norm that's just length normalization with a learnable epsilon. Because we took out the learnable scales from LayerNorm from most of the modules, we make everything learnable by having this weight scale thing, and it has to be positive to prevent that oscillating sign problem that I mentioned. We fix a bunch of different problems with this activation balancer. We're detecting dead neurons. We're detecting values that are too small or too large. To make the learning rate schedule more interpretable and to make everything more predictable, we're limiting the root mean square value of all the non-scalar parameter matrices to 0.1. So we fixed the size of all the matrices. We're doing model warm-up in a different way. We have this we have this variable bypass of all the layers to help it to train, early in training to help it to converge. We have a new learning rate schedule with no warm-up, with a different formula. And we found that replacing swish with DoubleSwish is helpful. Oh, and that link there is just to the recipe in our repository that has all of these changes. We've actually made some further changes later on. So we're up to like prune transducer stateless 5 or 6 now, because we've improved the recipe in other ways, but this is the first place that we used all this. Okay, so that's pretty much my talk. We can now have questions. I think I've gone through it a little bit faster, but maybe it'll help us to get back on schedule. That link is to a WeChat group for discussing Next Gen Caldi. If you're interested, you may be able to get one of these T-shirts. And those are just links to our main the main links, our main open source repositories. We have other ones too, but probably Icefall is the top level, you know, the recipes, and then that will download the other ones. So let me try to find the correct window so I can see if there's any questions.